So hello guys, today we are going to discuss about partitioning or sharding. So basically what the partitioning or sharding is. So um, like in replication, we store multiple copies of data on a same node, and we create master and slave replicas. For example, we have some data to be stored and then we create slave nodes of that master node that we say as a leader and follower based replication. But in sharding, we break the huge data into different to be stored on different nodes. For example, if this is a very big data, we store all we break this data and we store on the different nodes. So this is what we say as a sharding or partition. And there are different names to the sharding, like in MongoDB, we say it as a shard. In HBase, we say it as a region. Then in Bigtable, we say it as a tablet. In Cassandra, we say it as a vNode. And in CouchBase, we say it as a vBucket. All are different names of a shard or a partition. So how partitioning or sharding helps in achieving scalability? So this is one method to achieve scalability. I'll just describe what scalability is. That if the load on the system increases, the system scales itself to serve the new load and doesn't come down. So here what happens is we have different partitions on the different nodes, and whenever uh, the huge load or the query load increases on the different partitions, and the load is actually spread across all the nodes. So if we were having 10 requests earlier, now we have 100 requests. So those 100 requests are shared across all the partitions or all the nodes. And this means that these 10 nodes are able to handle 10 times more traffic as compared to one node. So that is how on a bigger load, partitioning helps to achieve the scalability. Uh, So what are the different types of partitions or partitioning types? So first is partitioning by key range. So what does it mean is I'll just have a notepad maybe, or I'll just open a paint rather. Uh, Let me just open the paint. Give me a second. Okay. So what does this mean? Partitioning by key range. So we have each partition holding a key and a value pair. For example, we have this as one partition, or rather we can say partition 1, or we'll say node 1, right? And we have another node or another partition, that is node 2 or partition 2. And we have node 3 and partition 3. So what happens is that all the keys which are from A to E. So let me just give you an example here. All the keys which are from A to E are stored on partition 1. All the keys which are from F to O are stored on partition 2. And all the keys which are from P to Z are stored on partition 3. So this is how the key range partitioning technique works. And whenever a client wants to query any key that has a associated value with it, it goes to a particular partition if the client is aware that on which partition which key range is available. Otherwise, we have to place some uh, node in between which will provide the information. That we'll also discuss later. So advantage of this is pretty straightforward. All keys can be sorted. So if we assume that A is here and the range is up to E, then we can assume it's definitely there that B is also there. But the disadvantage of this technique is in certain cases this partitioning key range based partitioning will not work. For example, if we are having some IoT devices and those IoT devices are sending huge amount of data, and we have taken key, the timestamp as a key. So for example, if in some particular hour uh, there is huge data, so timestamps keys will be huge. So in that case, only one of the partition will be loaded while other partitions will sit idle. So in certain cases, this will not work. So another type of partitioning is using the hash of keys. So what we'll have is we'll have a hash function here in which we'll input the key, and we'll have a hash. And to every hash, there is a separate partition mapped. So hash function takes the key, generates a hash. Hashes are evenly distributed. Even very similar keys, different hashes are generated. And hashes points to the partition. So for example, let's see example here. So we have this key, we have this hash, and it maps to partition 0. Then we have this key, we have this hash, and it maps to this partition 2, and so on. So advantage of this technique is it reduced the hotspots. So let us go through the term hotspot. So let's go through the skewed first. What's meaning of skewed? So skewed is whenever partitioning becomes unfair. That is, let's suppose there are 5 nodes, and um, some partitions or some nodes get or queried more data, and while other nodes are querying, getting queried or getting less data. That's called skewed, and this makes partitioning very less effective, and this can lead to hotspots. So what is hotspot now? Now whenever the cluster becomes skewed, that is, one node is getting all the traffic while other nodes are sitting idle, so in that case that one particular node will become a hotspot. So for example, uh, all load ends up on one partition. So 9 out of 10 nodes are idle, and bottleneck is only one busy node. So this is like disappropriation, or we can say this node is a hotspot. Okay, so advantage of hash-based hashes of keys is that it reduces the hotspots. How? That for very similar keys, we are um, generating, we are for very similar keys, we are generating different partitions. So that means what? If two timestamps are very near, still we have different partitions. Hence, the load is distributed evenly across the partitions. But the disadvantage is that, so the first disadvantage is here the sorted order of keys is lost. So earlier we have discussed that A we have, then we have B, so the keys will be sorted here. But in this case, all keys will be unsorted, right? And still we cannot get rid of all the hotspots. So for very like for milliseconds of time difference on a key, we can have same partition pointed by the hash of the key. So still the chances of hotspot creation exists. Then there is another kind of partitioning which is called partitioning with reverse or secondary indexes. So what is the reverse or secondary indexes? Let us see here. So indexing is basically a technique which is used to search the data in the database faster. So there is a kind of a forward index in which we store a key and offset, and based on the key we can just directly go on to the uh, offset, and then we can find the data. For example, we have key as here this and value is this. So we have this table, offset table we can say. So in a database we search the key, and then we'll directly jump onto the address and find the data. So, but there is a separate indexing called the reverse inverted or the secondary indexing. What happens is that in the database, we maintain um, like mapping from the mostly used words or the keywords to the indexes. So, to the keys rather, I can say. So, for example, we have the primary key index here, that key is this and value is this, key is this and value in this. But in the secondary index, we have taken this red, that is color red, and created a reverse mapping. So color red points to 191 and 306. So it points to 191 and 306. So if somebody wants to look for a red car, he can just directly go on to these keys. So he doesn't have to go to every key and then and then look at a value, every key then look at a value. So this becomes very much faster. And often this is the case in the daily life, right? We want to search for the red cars, or we want to search for the keywords rather than in place of keys. So, what is partitioning based on reverse indexing? So, first is node per indexing, that every node, uh, so let me go back here. So, every node in a partition, like every node, partition 1, partition 2, partition 3, it stores its own indexing. So, indexing happens here, secondary indexes. So, for example, partition 0 holds this, partition 1 holds this, and this is how we achieve partitioning based on the reverse indexes. The second is, but the disadvantage would be that if someone want to search a keyword, for example, if someone wants to search a red car, he has to go to every partition and look at the secondary indexes everywhere. For example, if I want to search a red car, I have to go to this partition, then to this partition, and then so on, n number of partitions I have to search. And again, if the database gets updated, then the secondary and primary indexes get changed. In that case, again, I have to search all the partitions. So the solution to it is global indexing. What does this mean? That we maintain or we store the indexes. Instead of storing the indexes at every partition, we construct a global index that covers all data in all partitions. So if what's the case if we store red and this red here on this partition, or maybe some other partition, only on the one partition rather than going on to all the partitions? So in that case, a person um, will not have to traverse to all the partitions. So this is shown in this figure here. So the red color, the red, the second index, that is the red car color, is stored on the partition 0. So 191 and 306 belongs to partition 0, while 768 belongs to partition 1, and that entry is also stored here. Similarly, the other things like color from A to R from all partitions can be stored on partition 0, while colors from S to Z can be stored on partition 1, right? But the disadvantage of this approach, global indexing based partitioning, is that uh, it's slower and complicated. The writes are slower and complicated. How? That whenever we want to write something on any of the partition, then it will affect the different partitions. For example, if we change this here, right, so it has to go back and update this partition, right? So if we have red entries on all the partitions, so we have, if we update single partition, it has to update this partition. And again, if this partition is replicated, that is, this data is stored on some other partition as a slave, then that data will be also changed. So, okay, let me just go to the replication part as well. Partitioning with replication. So what happens is that even partitions need to be replicated. Every partition has to store multiple copies of data for the fault tolerance. For example, if node 1 has three partitions, that is partition 1, partition 2, and partition 3, and partition 1 serves as a master copy of the data, while partition 1 data is stored on node 2 as a slave. Right, so this node can act as master in one case, while it can act as slave to store the copy of other partition. So this is how the partitioning with replication works. Now let's go to the rebalancing partition. So what's meaning of rebalancing partitions? That if any partition fails, that if any node goes down, and it'll happens, right, in a cluster of 1,000 nodes or in a cluster of 100 nodes, some nodes goes down, right? So in that case, how to move the data between the other nodes, right? So if one node goes down, some other node has to come up, and that data has to be copied. So we have the strategies for rebalancing. This means rebalancing partitions. So first technique is fixed number of partitions. That is, we create more partitions on one node. For example, if we have node 0 here, we created 5 partitions. If we have node 1 here, we created again 5 partitions. And when a new node comes in, so for example, there are only 3 nodes above, and new node comes in, node 4, it takes some of the partitions from existing nodes, for example here. Then we have the dynamic partitioning. So dynamic partitioning happens in HBase and Rethink database. So what happens is, if partition size grows above a threshold, for example, HBase has a threshold of 100 GB. If partition size grows above, 10 GB, if partition size grows above 10 GB, then it itself breaks into 2 partitions. And similarly, in the reverse order, if partition sizes shrinks below a threshold, then it's merged with the adjacent partitions. So advantage of this dynamic partitioning is it adjusts to the load, but um, the disadvantage is until the first split happens, the first partition takes all the load while other partitions sit idle. Now, what is the request routing? So request routing means that how we are going, like how a client is going to decide on which partition it has to send the traffic. For example, these are the nodes, or these are the partitions, and client is sitting here and it wants to search for some data in the node 4. So how will decide that on which node it has to send the request? And that's a very important question, right? So we have the first technique is round robin, in which the clients is allowed to contact any node via round robin load balancer in front. And if node owns the partition in which the client wants to query, then it handles. Otherwise, it forwards the request to appropriate node. For example, this one. So client searches for foo and chooses the node 1, and foo lives on node 2. So node 0 queries node 2 to serve it from its database or something, right? And it sends back to the client. Then routing tier first. So in routing tier first, we have a node in between that is called a routing tier. Um, and the client sends all the requests to routing tier first, and it determines the node that should handle and forwards it accordingly, right? So something here. This routing tier is aware that where the foo is and it sends it. And then the client direct connect. So the client is aware of partitions and assignment of partitions to the node. Now the client has this intelligence and it can send directly. But the point here is, are these 3 approaches good? So just pause this video for a second and think that what's the problem in these 3 request routing approaches? So right, thank you. So the problem with these 3 approaches is that the routing decision making component. So routing decision making component, here is a client, here is a routing tier, and here are these separate nodes. Uh, so if any change happens on the partition, so how this routing making decision making component is notified. So for example, if the data is moved from this node 2 to some node X, so how this routing tier is um, like notified, right? The changes, like about the changes in partition to the nodes. So we have a separate solution. We say that node as a zookeeper. So we can place, we can say it as a coordinator service. So this coordinator service will keep track of all the cluster metadata. So this partition, this node and IP address. So these are the partitions and these are the key ranges. So Zookeeper will keep all the metadata mapping of keys to node, and every node in the cluster will register to the Zookeeper. So whenever a partition or a node comes up, it has to register to the Zookeeper. And this concept of Zookeeper is used by LinkedIn Helix, HBase, Kafka, and Solar Cloud as well. So right guys, so this is all about partitioning um, or sharding, we can say. Uh, and thanks a lot. Have a good day. Bye bye.